So, as an application of this theorem, Bayer category theorem, I want to show that the set of irrational numbers cannot be written as a union of closed subsets, countably many closed subsets with empty interiors. Well, uh, of course, we can do this to Q, so that's the point, right? Q can be written uh, like that. I mean, union of closed sets with empty interiors, and I have countably many of them. All right. Well, so solution. So let P uh, be like this. It's contained inside this union. Okay, where each En is a subset of real numbers. Each En is closed with empty interior. But then you see Q is already contained in this union. So hence R, which is P union Q, right? Irrationals and rationals. And this is contained in this union. Okay. And Q is contained in this union. Uh, and this thing is, of course, since all of them are contained in R, we have this. So that R is equal to this union and this union. And this is a countable union, which is a countable union. Union of closed subsets, because each En is closed, each one-point set is closed. Therefore, this is a countable union of closed subsets uh, where with empty interiors, and each one has empty interior. But this is a contradiction. This is a contradiction, since R is complete, right? A complete metric space cannot be written like this, okay, by the Bayer category theorem. So I take in this case the subset E to be the real numbers itself by the Bayer category theorem. And we arrived at this contradiction because of the following assumption, that we assume that P is contained in such a union, okay, where each En is closed and has empty interior. Thus, the set of irrational numbers is not contained in a union of countably many closed subsets of R, of course, with empty interiors. Okay. All right. So that's the end of what I'm going, what I planned for Bayer category theorem. Now, let's pass to the final topic we will cover in this course, so-called Arzela-Ascoli theorem. I'll not be able to, finish discussing this theorem today. First, I have to give you some preliminary stuff. Okay. We know what. Recall that for any set X, non-empty set, of course, the metric space of bounded functions on X, which we denote by Bx with the supremum metric, right? The sup. This is a complete metric space. Is a complete metric space, and if X is itself a metric space, if X is already a metric space, then of course this is again a complete metric space. This result is true for any set. We don't need any structure on X. Okay, for any set X, the set of bounded functions is complete. But if X is already a metric space, then we may talk about, for example, continuous functions on X, right? And in that case, is already metric space, then the subset Cx of Bx consisting of continuous functions. Of course, here these are real valued functions, right? Continuous functions. Is a closed subset. We proved this is closed, and thus Cx with the supremum metric is also a complete metric space. Okay, so for any metric space, so X is a metric space, and Cx is this, the set of all continuous functions from X to R. F is continuous and okay, I have to be careful, and bounded. Okay. Yeah, I should write this. Cx is not necessarily a subset of Bx, right? There are continuous functions which are not bounded. I should say this. Cx intersection Bx of, okay, so one has to be careful. Yeah, this is complete. F is continuous, and what we see is that Cx intersection Bx is complete because it's a closed set in Bx and Bx is complete. Okay. Well, in particular, if X is compact, is a compact metric space, then any continuous function f from x to r has maximum and minimum, right? Has extreme values. In particular, since it has a maximum and minimum, f is bounded. So dx is already a subset of bx, okay? Because any continuous function is necessarily bounded. Therefore, for a compact metric space, Cx with the supremum metric is a complete metric space. The Arzela-Ascoli theorem is about compact subsets of Cx. This is a complete metric space provided that X is compact, but we wonder, what are the compact subsets of this metric space, complete metric space? Since it is already complete, for a subset to be compact, we know that it must be both complete and pre-compact. And since this is already complete, compact subsets of this will be closed subsets, which are also pre-complete. Okay, pre-compact. Sorry. Closed subsets of this will be trivially complete, and if they are also pre-compact, then they will be compact. But pre-compactness of this function spaces is described by means of a kind of continuity, so-called equicontinuity in this case. So let me tell you about this equicontinuity. So to state the theorem, Arzela-Ascoli theorem, which describes us compact subsets of this metric space, I need a definition. Okay. Maybe I should write Arzela-Ascoli theorem describes compact subsets of Cx. Okay. First, we need a definition. Okay, here is the definition. Okay, a subset E of Cx is called, so these are just continuous functions. It's called equicontinuous. Equicontinuous if for every epsilon positive, right? A function is continuous if for every epsilon you find some delta and so on, right? But here it is more than that. You need to find a delta which works for every function. Also note that since I assume X is a compact set, this set of functions, continuous functions, are always uniformly continuous, right? So on a compact set, continuous and uniformly continuous are the same. So E consists of uniformly continuous functions. But now I ask another uniformity in the sense that for any epsilon, I will find a delta which works for all the functions in the set E. Equicontinuous if for every epsilon positive, there is some delta positive, so that uh, the xy less than delta implies f of x minus f of y is less than epsilon for all xy in X with this property and f in E. So I find a delta which works for all the functions, okay, in the set E. In this case, we call this family of functions an equicontinuous set of functions, okay? So this subset is called equicontinuous if this holds, okay? We know that every element of E is continuous, therefore uniformly continuous. So for each epsilon there is some delta, but this delta in general is a function of f, right? For each function you may need to choose a different delta, but in this case we claim that there is some delta which works for all the functions, okay? So that's something special. If you can do this, then we call this set a equicontinuous subset of functions. Okay. Let's see one example. For example, let xt be the compact metric space 0, 1 with absolute value metric, okay? A compact metric space. And so I consider Cx, so this is the metric space of continuous functions on the interval 0, 1, right? F is continuous. Of course, each continuous function on 0, 1 is uniformly continuous because the interval 0, 1 is a compact set. Okay, let's see whether you know, every subset of this metric space of continuous functions is equicontinuous. For example, consider the following set. So let En, okay, E be this set, Fn's from 0 to 1, 0, 1 to R, uh, where Fn is this function. Fnx is equal to n times x. So f1 is just the identity function, f2 is 2x, f3 is 3x, and so on, right? These are just some linear functions. We may ask the following. Is this set of functions equicontinuous? So is E equicontinuous? Okay. Can I find for a, if epsilon is given, can I find a delta which works for all fn's? Well, you see, the distance between fnx and fny is what? This is just nx and y, and this is n times x minus y, and you want this to be less than epsilon, but then x minus y should be less than epsilon over n, right? So this should be your delta. This should be your delta. But you see, your delta, if it should be like this, epsilon over n, but it certainly depends on n, right? So you cannot find a common delta which works for all of them, right? So the answer is no. It's no, okay. Uh, and this is the reason, right? Uh, if so, okay. Uh, to show that this set is not equicontinuous, so I have to do what? Equicontinuous means for any epsilon there should be some delta which works for all the functions. So if I can find one epsilon, so that for that epsilon there is no delta which works for all functions, then I'll be done. Okay, so let epsilon to be equal to 1. Then if delta is positive, uh, choose, then choose what? N, so that uh, n times delta is greater than 1. Okay. Now, if x, y are in this 0, 1 with okay, so all right, now let me do it this way. Now let x to be 0 and y to be uh, delta, okay, then, or maybe, yeah, let me do it this way, delta over 2, and let me choose this to be less greater than 2. Okay, then x minus y is less than, this is equal to delta over 2, which is less than delta, but uh, let me choose n0, but f n0 x minus f n0 y, which is what? This is just n0 times 0 minus n0 times delta over 2. So this is just n0 times delta over 2, but n0 times delta is larger than 2, so divided by 2, this is larger than 1, which is epsilon. So what we have obtained is this. If I choose delta to be, sorry, epsilon to be 1, then no matter what your delta is, provided that it is positive, I can find some n0 so that uh, there are points which are delta close to each other, but their images have a distance larger than epsilon. Okay, therefore, hence the subset E of this metric space of continuous functions is not equicontinuous. Okay, the reason is, of course, the following. You see, these functions have greater and greater, slopes, right? So f1 is this one. All right, let's say this is 1 and this is 1. f1 is this. f2 is this. f3 will be with even bigger slope and so on, right? So they have steeper and steeper graphs. Therefore, uh, a uniform delta will not be enough to make all of them continuous at the same time. For each function, you need to choose your delta accordingly, okay? Because their uh, slopes are getting bigger and bigger, okay? So even with this metric space of complete metric space of continuous functions on the interval 0, 1, right? This is one of the um, simplest uh, simplest metric space of functions. It's a complete metric space. Functions are very nice in functions on the 0, 1 interval 0, 1. But even this uh, complete metric space contains subsets which are not equicontinuous. So this equicontinuity is something really important. Okay, it's an important assumption. And let me uh, describe the theorem. Arzela-Ascoli. Okay, so let xt be a compact metric space. Be a compact metric space. As the previous one. Continuous function, the interval 0, 1, right? The interval 0, 1 with absolute value metric is a compact metric space. We describe pre-compact subsets of this. A subset E of Cx. This is a compact metric space, right? Not compact, complete metric space, right? Cx is a complete metric space. This is pre-compact. A subset is pre-compact if and only if it is equicontinuous and bounded. So this will be pre-compact if and only if it is bounded. We already know that a pre-compact set is bounded, but not the other way around, right? A bounded subset need not to be pre-compact. In this case, it is sufficient that we assume the subset also equicontinuous, okay? If it is equicontinuous and bounded, then it is pre-compact. Of course, consequently, we have this. Consequently, this set is compact. Compact means complete and pre-compact. Since this space is already complete, its complete subsets are just closed subsets. So if E is already closed, is also closed, then it will be complete. And if it is equicontinuous and bounded, then it will be also pre-compact. And the pre-compact set, which is also complete, is compact. So it's compact if and only if is closed and equicontinuous. Right? If it is equicontinuous, closed, closed, bounded, and equicontinuous. E is closed implies E is complete because Cx is complete, and E is bounded and equicontinuous implies E is pre-compact, and we know that in a metric space, compactness is equivalent to completeness and pre-compactness. So if a set is both complete and pre-compact, then it is compact. So that's the theorem we are going to prove. Let me just tell you this. Note that in a metric space, a subset in a complete metric space, let me say. A subset is compact if and only if it is uh, closed and precompact, because closed subset of a complete metric space is already complete. Therefore, thus it is enough to prove it is enough to prove the uh, first assertion. Okay, so we just need to prove this. A subset is precompact if and only if it is equicontinuous and bounded. The second statement follows from the general stuff we have seen so far. Okay, let me stop at this point. Let me prove the theorem next time, because it will take some time. Yeah, it's not something short. I don't have enough time for the proof. Let me stop at this point and then discuss the proof next time.